the title seems to be quite provocative, since I thought everybody took the equations of conformal field theory seriously. So I would be very interested to find out what we didn't take seriously about this article. Can you hear me?
How about now? Okay, good. So it's nice to be here for what promises to be a very nice conference. So my talk is going to be about CFTs in dimensions, mostly in dimensions bigger than 2. So how do we normally define CFTs in dimensions bigger than 2? Well, most often we define them as endpoints of renormalization group flows, right? So this is the standard way to think about CFTs. We start from some theory in the UV, and in the simplest case, that's going to be a free theory, just some free stuff, free particles, and then we add a relevant perturbation to this theory, which destabilizes it. So it starts the RG flow. So we flow, 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 and we end up in the infrared conformal fixed point, right? And let me just give you some examples of this picture. So, for example, if you have a gauge theory in D equal 4, then for a particular number of fermion species, this theory develops a conformal fixed point in the infrared. And in this case, the UV CFT is just free theory of quarks and gluons, and perturbation, the relevant perturbation that we add is a gauge coupling. And another example is AON model in 3 dimensions. In this case, the CFT in the UV is even simpler. It's just n free scalars. And the perturbation that we add is a combination of the mass term, preserving the n symmetry, and the quartic coupling. And for a particular relation between these 2 perturbations, so for a generic choice of these perturbations, you are going to reach a massive theory in the infrared. But for a particular choice of these 2 perturbations, you are going to reach a critical, a non-trivial infrared fixed point, CFT. And that's the same conformal field theory, which for n equal 1 describes the critical point of the 3-dimensional Ising model. So this way of defining CFTs through the RG flows, it's very good. It's a very good and very powerful way of thinking about conformal field theories, and about thinking about which phases are possible in your space of parameters. But in practice, it's not, being able to define something is not necessarily being able to compute something using this definition. And okay, there are cases where this definition, this RG definition actually can be used to compute things. But in other cases, when the conformal fixed point is strongly coupled, it works in practice not as well. So for example, just to give you an example, for this first case, where exactly the boundary of the conformal window is, so how many fermions do you have to add to have a conformal fixed point, and beyond which number you're going to have a conformal fixed point, and below which number you're going to have confinement and chiral symmetry breaking. After many, many years of work on the lattice and in theory, it's still not known. So people are still arguing whether it's 10, 12, 9, whatever. And later on, we will see what the situation is for the Ising model. So, but there are also conformal field theories which do not have an RG definition. And the most famous example of such a theory is the n=4 super-Young-Mills. So we know that that theory is conformal for any coupling. And this means that this theory doesn't flow. You fix the coupling, and the theory just sits there, it doesn't flow. So how do you define such a theory? The fact that you have a Lagrangian, okay, it makes you feel safe, but it's not necessarily a definition, because it would be a definition if perturbation theory were convergent, and for some quantities it probably is, but probably not for all quantities. So, and then there's another example which is even more dramatic. It's the 2,0 theory in 6 dimensions, which describes the dynamics of multiple M5 branes. And that theory, it cannot be defined, or at least we don't know how to define it as an endpoint of RG flows, simply because in 6 dimensions, whatever free theory you take, it doesn't have relevant deformation. So you can't even start an RG flow from the UV. So we need another definition of conformal field theories in higher dimensions, both for practical reasons that on the first slide, and for reasons of principle on the second slide. And so what definition shall we take? Well, we'll take a definition which has been successful in 2 dimensions. So here I'm going to formulate it in 3 dimensions. Well, that if it's an imaginary coupling, you can, but it's going to be a non-unitary theory.
Well, maybe it has a unitary fixed point.
No, the fixed point of that theory is known. It's not. Well, it's the theory which describes the Lie-Yang transition. It's the branch which connects to the Lie-Yang fixed point.
It's 6 dimensional, or was it 2 dimensional?
Well, it exists all the way from 2 to 6. So here's my definition. Well, not my definition, but and I'm very proud of this slide because this is a string math conference, and I managed to squeeze in all these mathematical words on the slide. So CFT for this talk is going to be a commutative associative algebra of local operators. and so this is going to be a CFT in flat Euclidean d-dimensional space. And so the plan of my talk is going to be first to remind us what is the meaning of various words in this definition, and then to show you that this definition is actually not vacuous, even if dimension is bigger than 2. Right? So let's start with local operators. So the local operators in the conformal theory are characterized by their quantum numbers. And there are 3 quantum numbers for each local operator. So the first one is the scaling dimension. The second one is the representation of the rotation group in which this operator transforms. It's basically the number of indices of this operator, whether it's a scalar, a vector, a tensor, and so on. And then finally, if your conformal theory has a global symmetry, which most often it will, then you should, for economy of thinking, you should classify all operators into a irreducible representation of your global symmetry group, right? So the collection of these numbers is called a spectrum of operators, right? And then, again, for economy of thinking, we divide all operators in a conformal theory into primary operators. These operators transform homogeneously under the conformal group, and the rest are the descendant of operators. These are the derivatives of the primary operators, and so they just go for the ride. You don't have to analyze them separately. While the primaries are the ones we focus on. And so, of course, in 2 dimensions, there are also Virasoro primary operators, which transform homogeneously under the Virasoro algebra. But those ones are not available in higher dimensions. And the primaries are called quasi-primaries in 2D. Now, OK, to show you that all this theory is actually can be used to describe a real-world phenomenon, here is a spectrum of low-lying primary operators in the critical point of the 3-dimensional Ising model. So you see here I list various operators. So these are just names. And for each operator, I give its spin. So here, the operators are all symmetric traceless tensors of a given spin. So there are scalar operators. There's a spin 2 operator. In this table, spin 4 operator. Then there is a global symmetry of this theory is Z2. It's just the spin inversion, which flip the spin flip symmetry. So there are operators which are Z2 odd, and there are operators which are Z2 even. And then in this column, I give scaling dimensions of these operators to the precision that they are known. And this precision comes from the randomization group. So from various techniques which are ultimately based on the randomization group, like the epsilon expansion and so on. And you see that, OK, for some quantities, precision is impressive, like the dimension, for example, of the lowest lying Z2 odd scalar field, the so-called spin field, is known with impressive precision. But as you go up, the precision gets worse. The lowest lying epsilon, the Z2 even scalar, also is known with a good precision. But we should realize that the numbers in this table are presumably just as fundamental constants of mathematics as pi or e or Feigenbaum constant and things like that. So it is pretty unforgivable that we know about this theory for many, many years, and we still don't have an algorithm which would allow us, at least in principle, to determine these constants of nature with arbitrary number of digits, right? So that's what we are about. That's what we are after. So, OK, what should I add about this table? OK, these exponents, these are the critical exponents, the experimentally measurable critical exponents of the three-dimensional Ising model. You know, then in the StatMath literature, they usually quote these exponents, but you can always translate into the dimensions. So what else can I say? In this table, there is one operator which has a protected dimension. It's the stress tensor operator. And, well, it's the property of, it's the locality of the three-dimensional Ising model which guarantees that there is going to be a stress tensor operator. If you wish, we can add the existence of stress tensor as an axiom. But in principle, there are also interesting CFTs which do not have a stress tensor. So one should keep this in mind. And OK, here there are only 7 operators, but in principle, there are going to be infinitely many primary operators and infinitely many operators for each spin, and nothing is known about them. So all literature of the three-dimensional Ising model just condenses to these 7 numbers. OK, let's go ahead. So as I said, the operators of the CFT, they form an algebra. And in physics, this algebra is called operator product expansion. So surely you have seen this. So if you take 2 operators which are getting close to each other, then I can replace the product by a sum of other operators multiplied by certain polynomials. Well, it's not polynomials. These are power series in the distance and the derivative, which are completely fixed by conformal symmetry. That's the beauty of conformal symmetry. And the coefficients in front of these polynomials, they are not fixed. So these are the parameters of the theory, and they are known as OPE coefficients. So this is just pure numbers. And associativity of this algebra means that if you take a product of 3 operators, you can take the product of O1 and O2, or you can first start with the product of 2 or 3, and you should get the same answer. And schematically, once you expand it, it means that you are going to get a kind of constraint which is quadratic in the OPE coefficients, which has to be satisfied for all operators appearing in the expansion. So this is the kind of constraint we have to be dealing with. And why associativity? Well, because in a quantum field theory, the main class of observables are correlation functions of local operators. And using this algebra, this operator product expansion, repeatedly you can take an endpoint function, you can reduce it to n-1 function, or rather sum of n-1 functions, and so on, up to when you arrive to one-point functions. Those are fixed by normalization and conformal symmetry. So the unit operator has one-point function 1, and any other operator has one-point function 0. So associativity just means that when you do this operation, there are many ways to do this operation, and the result should not depend on the order. So it's forced on you by this physical requirement. So I'd like to add a disclaimer that in principle CFTs also have other observables, not just the correlation functions, but non-local observables. These are called conformal defects, and some of them are very famous, for example, Wilson loops and conformal gauge theories. But I'm not going to discuss these observables today. So there was some interesting recent work on this topic. And I'm also not going to discuss other constraints on conformal theories which may come, which almost certainly come, and from considering the theory and putting it in a different background, not in flat space, but in some curved background or maybe in background of different topology. So this is kind of modular invariance type constraints. And very little is known about these constraints in dimensions bigger than 2. So we know that these are fundamental for d equal to 2, but above, very little is known. So for me today, the CFT is really going to be defined by the conformal data, so by the spectrum of operators and by the OPE coefficients. And on this conformal data, I put a constraint of associativity. So that's the definition of the theory, or at least the good 0th order approximation to the theory, necessary condition. And a very old idea of conformal bootstrap, which goes to Ferrara, Grillo, and Gatto, and Polyakov, says that if you impose associativity on the set of conformal data, then this should, in principle, fix the theory up to discrete number of choices, or maybe finite dimensional families of choices, and so on. So that's this is a very old idea, and actually this idea has been used with success in two-dimensional quantum field theory, conformal field theory. So minimal models have been solved this way, and the Liouville theory has been solved this way, using some extra two-dimensional tricks, but basically using this philosophy. And so what I would like to show today is that this idea can also be useful in dimensions bigger than 2. But before we go there, there's one technical point that I need to discuss, which is related to unitarity. So unitarity is usually defined in terms of the S matrix of scattering of particles and so on. And this definition of unitarity can be extended also to conformal field theories, which do not have particles. If you analytically continue them to Minkowski and maybe couple them to some external probes and so on. But there is a better definition of unitarity which is more efficient for conformal field theories, and that's the one that I want to discuss. And it's related to the concept of radial quantization that we need anyway. So in radial quantization, the way I view radial quantization is by slicing. So when you slice the theory, when you slice the space by the sphere centered at some origin, which is arbitrarily chosen, you can do a Weil transformation from your flat space, which puts the metric into the form of a cylinder. So by the cylinder, I mean SD-1 times R. So these two spaces are Weil equivalent. And the coordinate along the cylinder, the tau, is the log of the radial coordinate in flat space. So under this transformation, the dilatation generator in flat space around the origin goes into the Hamiltonian along the cylinder. Now, the fact that you can take any conformal theory and you can consistently lift it to the cylinder or transfer it to the cylinder, well, it's, if you wish, it's the most powerful axiom of conformal field theory. Like if you want to take just one axiom of conformal field theory, take this one. So it was realized long ago. It goes back to work of Mach and Lucier in the 70s. But basically, if you take this axiom, then everything else follows. For example, the state operator correspondence of conformal field theory, which says that any state in Hilbert space on the sphere can be expanded into a basis of states which are which are obtained by applying this local operator centered at the origin on the vacuum, this is the consequence of this axiom that you can consistently formulate the Hamiltonian dynamics on the cylinder. And in fact, the operator product expansion also is a consequence of this axiom. So let's keep this in mind. There is this cylinder, but the reason why we need the cylinder is for the unitarity, I said. And so on the cylinder, there is a very natural definition of norm, which comes as follows. So if you take a certain number of operators inserted at different times, different cylinder times, and acting on the vacuum, this generates for you a state which lives at a certain cylinder time, let's say time equals 0. And then the norm of this state is going to be the overlap of this state with the other state, which is obtained by inserting the same operators in a mirror symmetric way. So, so here you insert them tau 1, tau n, and the mirror symmetrically you insert them at -1, -tau 1, -tau n. So when you do this, so you consider this correlation function has to be positive in unitary theories. And this is the Euclidean space version of unitarity, which is called reflection positivity. So that's why we go this way. And now, so unitarity requirement says that all norms have to be positive. So you fix an orthonormal basis of primaries in which every primary has a norm 1. And then you have to impose that the descendants of the primaries, which are just acting on primaries with p's, also have to have a positive norm. So you just have to evaluate this sort of correlation functions, and everything here is fixed by the algebra. And so this gives you, so what this boils down to are just constraints on allowed primary dimensions. And so these constraints have been worked out a long time ago in the 70s. And for example, they are called unitarity bounds. And for example, in d equal to 4, they say that if you take a representation J1, J2, then the dimension has to be bigger than this or this, depending whether you have one of J1 0 or not. So the reason, so because of this sort of constraints on dimensions, the unitary theories are more tractable than general theories. So in this talk, I'm going to focus on unitary theories, but one should keep in mind that there are many interesting CFTs which are non-unitary, like the ones that Nikita mentioned. So we'll have to get back to them at some point in the future. Okay, so any questions? Now we go back to our OP associativity. So we have to master this constraint, which says that if you take the product of 3 operators and we take first the product here or first the product there, then the answer is the same, right? And so the way we are going to express this constraint is by taking a scalar product with the 4th operator, right? So this part will have expansion in OL. So let's take a scalar product with OL to project on that direction. And then we get the following constraint, that a 4-point function OI or J or KOL, if you take the OPE in this way or in another way, it has to give the same answer, right? For any pair of operators, for any 4 operators I, J, KL. Very good. Well, this would be dealing with this equation would be dealing with the full conformal bootstrap system. So this is at the moment not known how to do. And in this talk, in the rest of the talk, I'm going to consider the simplest case where all these 4 operators are identical scalar primaries. So I'm going to take them all equal. And the fact that they are all equal is not so important. It will be easy to relax. And in fact, I'm going to show some results where these operators are not equal, but for example, members of the same global symmetry multiplet. And one can even consider the case when they have unequal dimensions. That would not be a problem. The limitation that they're all scalars, that would be possible, but more difficult to relax at present. So we will see later what this limitation is due to. So this is now going to be the simplest bootstrap equation, the simplest of them all. And this comes from considering a 4-point function of 4 scalar primary operators, which by conformal symmetry is fixed in terms of some unknown function of cross ratios, GUV. And when writing this equation, I chose an arbitrary pairing, 1, 2, 3, 4. I can do it with the other pairing, and the answer has to be the same. So this is crossing symmetry, and this means that this function GUV has to satisfy this functional equation. So GVU, so when you interchange the order, it's related to GUV times V over U to the power delta sigma. So you see that the delta sigma enters into this equation. Very good. But now, in order to write, so this is going to be our equation, but in order to turn it into a true constraining equation, I have to find an expression for GUV. And this I'm going to do using the OPE. So let us take the OPE of 2 sigmas, which is going to contain a certain number of primaries in the right-hand side with unknown coefficients. And in this case, there's a simplification that these primaries, first of all, they can occur only in the symmetric traceless tensor representations of the rotation group. So you cannot have like antisymmetric tensors or anything like that appearing because of group theory. And also, because of both symmetry, only even spins will occur in this OPE. So that's a simplification. And now, since you can do the OPE in the 1, 2, and the 3, 4 channel, you can reduce this 4-point function to 2-point functions of these operators OI times some coefficients which are completely fixed by conformal symmetry. And so this means that this function GUV will have an expansion of the following form. So it's going to be 1, which comes from the contribution of the unit operator, plus some of these coefficients squared, times some functions of U and V, which are called conformal blocks. Right? So these conformal block functions are completely universal, completely fixed by conformal symmetry functions, which depend only on operator dimensions, so depend on the dimensions of y, on spin OI, and on the space-time dimension. So in fact, if you are familiar with the two-dimensional story, in the two-dimensional case, when you express this equation in terms of Virasoro primaries, then these conformal blocks also depend on the central charge of the theory, right? Of course. But here we are in general number of dimensions. And notice that these conformal blocks are going to depend analytically on D. And so you could even consider this whole story for fractional number of dimensions. So if you ever wondered that that the field theory in 4 minus epsilon dimensions, is it just a formal trick to get to the 4-dimensional theory, or is it really mathematically well defined? Well, this is the definition of conformal field theory in fractional number, in any number of dimensions. Just consider this equation that GUV given by this sum satisfies this crossing symmetry constraint. So this is the definition of the theory. Of course, you also have to impose infinitely many other constraints having to do with other fields, but here we're considering just one of them for simplicity. Well, there are some special number of dimensions where the presentation theory changes, of course. So you have to think a little bit how to do this. So I don't think it has been done systematically, but I think it can be done. So for example, the fact that the Ising model exists everywhere between 2 and 4 dimensions, which is something that condensed matter physicists have always been telling us, I think that statement is should be mathematically well defined. Okay, so let's go ahead. So here we have these conformal blocks, and if you want to make progress, you have to have good control over these beasts, these conformal blocks. And in fact, we do have good control over these blocks, and the way to analyze them is actually the best way to analyze them is not in these U and V coordinates, which we normally use, but in these polar coordinates, which are introduced as follows. So you take these 4 operators and you insert them, so these 4 operators, sigma 1, sigma 2, sigma 3, sigma 4, you can, of course, move them around by applying conformal transformations as you want. And you can apply a conformal transformation, first of all, to put them all in a plane. And then you still have some freedom to move them around in this plane. And why don't we put them in the following way? So we put them symmetrically with respect to the origin. So we put sigma 1, sigma 2 symmetrically, and sigma 3, sigma 4 also symmetrically. So this configuration has, once you scale everything, it has only 2 parameters. It has the distance from sigma 1 to the origin, which I call r, and the angle, theta. So these polar coordinates, let's use them to parameterize the conformal blocks. Then there's going to be some transformation between u and v and r and theta, but never mind. That's clear. And so when you take this configuration and when you do Weyl transformation to the cylinder, then you find the following picture. So there are 2 operators, sigma 1, sigma 2, inserted at some time tau, and 2 operators inserted at some other time, and they form a relative angle. That's going to become important in a second. But for the moment, notice that if we take sigma 1, sigma 2, and we apply it to the vacuum, then this state is going to have, by state operator correspondence, an expansion into some states produced by local operators acting on the vacuum. These are the states Ek. And the energies of these states, so I'm going to group all these states according to which primary operator they are descendants of. So the energies of the states are going to be of the form, the dimension of the operator, of the primary operator, plus k, which is the level, the descendant level. So these coefficients, the coefficients in the second sum are universal numbers fixed by conformal symmetry, while this is the OPE coefficient, which we don't know. And now if we take this state and we take the same expression for the state produced by sigma 3, sigma 4, and we take a scalar product, then we get the following formula. So of course we will get the product of the OPE coefficients, and then here we get a sum, so the squares of these universal numbers, and then here we have this power of r, and this power of r has a very clear physical meaning. So so this power of r is nothing but e to the power minus energy of the state times the Euclidean time that you have to evolve. So when we do quantum mechanics in the Euclidean signature, then of course to evolve a certain state Euclidean time tau, you have to pay a factor e to the minus tau times the energy. And then finally, you have to account for the fact that this state is rotated with respect to this state by angle theta. And when you propagate a state of a spin L in d dimensions, then the dependence on the angle theta is given by the Gegenbauer polynomial. So this is just a known polynomial of degree Lk, and very easy to compute. And it has absolute value less than 1. So in this formula, so by the way, in this formula, this second sum is the conformal block expressed in these coordinates. So if you are to find the conformal block, you just have to compute these coefficients dk, and it's very easy to compute them. There are some recursion relations which generate these coefficients. Not unlike Zamolodchikov's recursion relations, which I'm going to mention in a second, but actually simpler than that, because in d dimensions, these conformal blocks, they satisfy a certain PDE, while in two-dimensional conformal blocks don't satisfy any simple PDE. So you can find these coefficients, and the moment you found them up to some very large k, this series converges exponentially fast. So you don't, if you are a practical person, if you just want to evaluate these blocks numerically, no problem. You can easily do it. These are some complicated special functions, but completely under control. So I just want to add the comment for people who have been working on the two-dimensional conformal blocks. And you know that in 2 dimensions there is this z coordinate, which is sometimes very natural for working with conformal blocks. And the z coordinate is introduced by putting one operator at the origin, one at 1, 1 at infinity, and then it's the z coordinate of the one remaining operator, which is your z. And then in these coordinates, the conformal blocks have a cut which extends from 1 to infinity. So certain problems are, like especially if you are dealing with exact expressions for conformal blocks, they are best analyzed in the z coordinate. But if you're a practical person and if you want to evaluate these conformal blocks numerically, then it's been known since the work of Zamolodchikov from '87 that the best expansion parameter for the conformal blocks is actually not z, but this q. And this q has the property that, so it's the exponential of this uniformization variable, which uniformizes the Riemann sphere with 3 punctures and maps it on the upper half plane. And q is everywhere less than 1 in this upper half plane. So in these coordinates, so these coordinates cover the full region where the conformal blocks are defined, and the expansions obtained using these coordinates are the most rapidly convergent expansions. Most rapidly convergent. Actually, more rapidly convergent than the ones that I just represented, which are using this rho coordinate. So for general D, the best you can do is you can introduce this rho coordinate, which is just r to the I theta, where r and theta are the coordinates I introduced in the previous slide. And that coordinate, it maps the complex plane with the cut from 1 to infinity to the unit disk. So it doesn't uniformize the full Riemann sphere, but that's the best you can do probably in general dimensions because you don't have holomorphic structure. The conformal blocks do not factorize into holomorphic times anti-holomorphic function. So that's the point of this remark. Okay, so now that I showed you that conformal blocks are under control, let's go to our bootstrap equation, which is here, I wrote it again. It's this crossing symmetry constraint, which has to be satisfied by the conformal block expansion. And let's try to learn from it. And the strategy that has proved successful in this task so far is the following one. So in this equation, we have a sum over all operators appearing in the OPE. So let's make some assumption about the spectrum of operators appearing in the OPE. And I don't mean like a very drastic assumption. I don't want to like assume that my spectrum is only integer or anything like that. I want to make an assumption, for example, about gaps. So let's assume that there is no operator below such and such dimension, something like that. Or let's assume that there is no operator closer to the stress tensor than certain amount, something like that. Or maybe let's assume that certain OPE coefficient takes a certain value. And once you are making such assumptions about the spectrum, you try to solve this equation for these squares of the OPE coefficients viewed as variables. And you're trying to ask, does the solution exist or not? So this is a numerical problem. And in fact, most of this numerical exploration has been done numerically. And the keyword here is linear programming. But I'm not going to tell you how exactly we do it, but we do a careful job, although I'm sure there is still room for improvement with respect to what we are doing. But the main lesson that we learned so far is that this very simple equation, the very simplest of the bootstrap equations, is already surprisingly, very, very surprisingly constraining. So it teaches us already a lot. And so let me just show you a few things that it taught us. So this is just an example of a study about gaps. So I told you about gaps. So here I'm considering a CFT in dimension equal to 4. So I'm taking any 4-dimensional CFT, and I'm assuming that the global symmetry of this CFT contains an SON factor. Right? So let's just take any CFT with such a global symmetry. And n is a parameter that we are going to vary. And in this CFT, I'm going to consider an OPE of 2 fundamentals of SON. So I'm assuming that there is a scalar operator in this theory which is a fundamental of SON, and I'm taking this OPE with itself. And in this OPE, by group theory, there can be different representations of SON appearing. And for example, there's going to be a singlet, and there's going to be a symmetric traceless tensor of SON. And I'm going to focus on the ones which are the lowest dimension in this channel. And of course, I'm allowing all other operators, and I'm allowing all operators of spin 1, 2, and so on, provided they are subject to unitarity bounds. And I'm going to ask the question, what is the maximal allowed value? So fix the dimension of sigma. What is the maximal allowed value for the dimension of S and for the dimension of T? Like, is there a CFT where, for example, the dimension of S is arbitrarily large? Or is there a CFT where S is not there? Can you have a CFT in which there is no singlet in this OPE? Well, the answer is no. So here's a rigorous result about this kind of theories. Well, this plot is for n equal to 4, so SO4 global symmetry, but you can make it for any n. And so you see here, well, don't pay attention to these thin lines, just pay attention to these thick lines. And you see, so the claim is that any conformal field theory must have, so given a value of delta sigma, which is on the horizontal line, any conformal field theory in 4 dimensions has to have an operator T whose dimension is below this curve, and has to have an operator S whose dimension is below this upper curve. So this is a rigorous result about 4-dimensional conformal theories, which follows from this conformal bootstrap equation. So if the operator is not there, or if its dimension is above this curve, then we can show that this equation has no solutions, period. And so such a CFT is impossible. OK, let me show you another result about the central charge. So it's still in 4 dimensions. So suppose, again, we know this dimension sigma of the field sigma. And now I would like to say something about the central charge CT, which is the one, in 4 dimensions there are many central charges. It's the one which is proportional to the 2-point function of T mu nu, of the stress tensor. Well, not the most interesting one, but still it's the one I can say something about. And the reason why I can say something about this is that because the 4-point function of sigma contains in it a block, a stress tensor block, and the prefactor of this block goes like 1 over CT. So in the limit when CT goes to infinity, this is the limit in which stress tensor decouples. So this is the limit familiar in ADS CFT with decoupling gravity in the bulk. And in the limit when CT goes to 0, this coefficient blows up. And our experience shows that if you are doing something with this conformal bootstrap equation, which kind of distorts it too much, like imposing gaps which are too high, or if some coefficients be getting too large, then typically you are not going to find a solution. And here's what is happening indeed. So again, as a function of dimension sigma, I have this time a lower bound on the central charge. So I can show, OK, sorry, this is a crappy plot, but there are better plots in paper by Poland and Simons-Duffin. Just wanted to show a plot from my paper. So the claim is that any conformal field theory must have, given delta sigma, must have a central charge which lies below this curve. And you see, this is the central charge of the free scalar theory. And you see that, for example, you can argue using our bounds that in a certain range of delta sigma, necessarily the central charge of the CFT has to be bigger than the central charge of the free scalar theory. Well, then the bound gets not very good, but we don't know if it's physical or not. So there are results of this type. Now, there are also bounds. If you are interested in SUSY theories, there are also bounds for those theories. For n equal 1 SUSY, there are bounds on the dimensions of real operators, which are not accessible to the usual supersymmetry techniques. And for n equal 4 super Young-Mills, recently there was a work by Beam, Rastelli, and Van Rees, where they applied this analysis to the 4-point function of a protected scalar operator, the 20 prime. And in this operator, the Konishi, in this 4-point function, the Konishi operator appears, and it turns out that you cannot decouple it. So if you try to take the dimension of the Konishi operator too large, then the crossing symmetry is not satisfied. So you get an upper bound independent of the coupling on the Konishi operator dimension. Okay. And there was a paper today where they argue that this bound may be saturated at the S-dual coupling. But now I would like to say, like in the last 5 minutes, I would like to say something about the Ising model. So this is the bound. So now I'm going to the 3-dimensional case. And here I can also make the same sort of plot. So for here, the OPE sigma times sigma is 1 plus epsilon plus other operators. So I can make the same type of plot which shows what is the maximal dimension of epsilon as a function of the dimension of sigma. And you show that indeed there is an upper bound, so this is not a surprise after so many bounds that I showed you. And this is, by the way, in a paper that we've written last year with Shiraz Shok, Miguel Paulos, David Polon, David Simmons-Duffin, and Alessandro Vicky. But you see that this bound now shows a new feature. Namely, this bound has a corner point. And this corner point is actually where the Ising model lives. Well, this is the empirical fact. But if you blow up, then you find the following thing. You find that, so this is our bound, and this red rectangle are the best available determinations of the dimensions, sigma and epsilon, using the epsilon expansion and other techniques. And you see that it lies straight on our curve. Now, well, this is very suggestive, of course, and well, I was planning to show something here, but it's not showing. Well, in this plot, what this plot shows is that the same thing happens for the 2-dimensional Ising model. So again, if you make the same plot for the 2-dimensional Ising model, again you find that it lies at the corner point, except in that case you know exactly the dimensions, so you are much more confident that that's not an artifact of some approximation or not. And here, so the idea that we are exploring right now is the following. So here there's some allowed region, and in this allowed region there are plenty of solutions to the crossing symmetry equation. But when you go to the boundary, at the boundary the number of solutions to the crossing symmetry equation becomes reduced, greatly reduced. So this is some geometrical fact which unfortunately I don't have time to explain, but maybe it's even going to become unique. And you can test this idea in 2 dimensions, and that plot fortunately is showing. So in this plot, what we are doing is the following. We are studying the 2-dimensional Ising model, but without using the Virasoro. We are just using the global conformal invariance. So we are abandoning a lot of information which is normally used. So we are fixing the dimensions of sigma and epsilon to the values which are exactly known, but anyway, that's where the corner point is. So we basically found them as well. And then we try to solve for the dimensions and the OPE coefficients of all other operators appearing in this OPE. Of course, the spectrum is known exactly. So we try to solve and we can compare. And so in this plot, the blue bands are centered at the exact values of the Ising model operator dimensions. And the red lines, the thin red lines, are the numerically extracted values. And you see that we basically get like about 20 operators with their OPE coefficients right on the spot. And then for some subleading operators, the agreement is, okay, it's more or less, it's clear that there's something there, but the agreement gets a bit worse, But anyway, this shows the power of conformal bootstrap in determining, surprising power of conformal bootstrap in determining not just a couple of operators. Remember, everything we know about the Ising model are just 7 dimensions. And here, for the 2-dimensional case, we are able to, in one go, to determine 20 operators. So the goal is to do something like that in 3 dimensions. OK, let me just conclude. So I should have put this slide at the beginning of my talk, but I didn't want to finish to start on the negative note. So basically, the justification for this whole program is that we desperately need another method, a new method, to solve quantum field theories in higher dimensions. So what we have is has either limitations, either practical or computer limitations, and so on. And perhaps conformal bootstrap could be one of such techniques. And so why this method is nice? Because the equations that we are solving are mathematically well-defined equations, so they're convergent equations. You never have to massage divergent series to get some number out. These equations are very easy, actually, so to put on a computer and explore. So the plots that I showed you, you can, like in a matter of minutes, you can produce them on a laptop. It's not like supercomputer type of calculation that you need for lattice QCD. And so it is producing some results which are not accessible by any other means. And I hope that sooner or later somebody will find a method which will be able to solve this equation, not just extract some bounds from them and so on, but just to solve them. And well, there are a few directions that I think I still have time to say, right? Do I have? I have time. So, in the lack of this method to solve these equations, we can still continue learning gradually. So that's nice, something nice about this approach. So we can still continue learning gradually about these equations. So one thing that we are definitely going to do is the numerical determination of the spectrum of the 3-dimensional Ising model, something like what we did for 2 dimensions, but for 3D. Another thing which definitely has to be done is to see what changes, what improvements do you get if you add to the correlator sigma, 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 sigma other correlation functions. Because remember, bootstrap is about infinite number of 4-point functions put all together. Here we got extremely lucky that we are getting an incredible amount of information already from just one 4-point function. But we shouldn't forget about these guys as well. So there's some interesting interplay, and all ingredients are in place also for doing this analysis. Then more daunting task is to do the bootstrap for the correlation functions of conserved currents and for the stress tensor. And the reason here is that the conformal blocks for these objects are not as well known as conformal blocks for the scalars. There are many tensor structures, and you have to disentangle them, and so it looks a bit scary, but hopefully it can be done. It would be very interesting to do it. Then for SUSY theories, so I know that there is some work in progress for n equal to SUSY theories, maybe heading towards classification of n equal to SUSY theories, and by the Stony Brook group. And also, I hope that sooner or later somebody will just do this bootstrap for the 2,0 6D theory, because people are playing all sorts of desperate tricks like 5-dimensional Young-Mills and so on, which looks just a very circumspect way to get at this theory, which has no other definition but the bootstrap definition. And of course, one should always hope that there are going to be some unexpected developments as well. Those are the most interesting ones. Thank you.
Have a few minutes. Are there any questions? Surely there must be some curiosity in this group.
So you think that by having a small input of conformal dimensions, you will produce the whole spectrum?
Well, not even with input, because these dimensions delta sigma and delta epsilon can be determined as a position of the corner point. No input at all. No input at all. And then from that, you can determine all the operators which appear in the sigma times sigma p. But clearly, this is just something very special which is going on for the three-dimensional Ising model. Because we just stumbled upon it that the three-dimensional Ising model is, for some reason that we don't yet understand, lying at the corner point, at the boundary at the corner point. Why is that? We don't yet understand. But if you take this for granted, then we can use it.
For general conformal field theory, what is the minimal amount of information which you need to start?
For general conformal field theory, you could start it by knowing the global symmetry group and by knowing, say, the number of relevant deformations.
Just a number?
Well, that already is going to, presumably there is only a finite number of conformal field theories. Then you can try add bounds on the central charge, and presumably as you increase your net, you will get more and more points.
Would it mean that the theory is integrable? Or if the theory of the sphere is integrable? You can actually determine the...
It might be that the three-dimensional Ising model is integrable in some sense. Any CFT, no. No, I don't think it's integrable.
You say that you can determine the dimensions of all.
Well, it's determined, but not analytically. Right? It's going to be a systematic way to reproduce the dimensions with any desired accuracy. But it doesn't mean that it's integrable. Right? Oh.
Okay, with that, let's stack our space here again.